Our series of lectures on convection dominated flows continues. In the previous few lectures, we had looked at transport in the limit of high Peclet number, where convection is much larger than diffusion. We had first looked at the flow past a flat plate, for example, which is shown here. And in this case, we had taken the limit where the Peclet number is very large, that is UL by D is much greater than 1. In this case, we would expect if we just neglected diffusion altogether, the equation becomes U dot grad T is equal to 0. This kind of an equation implies that there is no variation in the temperature along the velocity direction, or there is no variation in temperature along the velocity streamlines. We considered first the simple problem of a flow past a flat plate, where for x less than 0, the temperature in the fluid was uniform, the ambient temperature T infinity. And for x greater than 0, we had imposed a temperature T is equal to T1 on this surface. Okay. So, this was the original problem, where we had a temperature T1 on the surface for x greater than 0, and because of diffusion, the temperature increases within the fluid. That is a heat transfer problem. If you neglect diffusion altogether, okay, you just get U dot grad T is equal to 0, and the temperature is a constant, and there is no way to satisfy the boundary conditions. And we had gone to the origin of the problem. Why is it not possible to satisfy the boundary conditions? That is because in this case we have neglected diffusion. Convection transports heat, mass and momentum only along the flow direction. At the surface, the transport has to necessarily be perpendicular to the direction, because transfer has to take place across the surface from the surface to the fluid. Transfer perpendicular to the surface cannot take place due to convection. So, ultimately, if we want transfer to take place perpendicular to the surface, that transport has to necessarily be due to diffusion. And therefore, we have to take into account the effect of diffusion in a thin region near surfaces which are heated or where the concentration is different. Near the surface, the concentration or the energy is being swept downstream by the flow, and it is diffusing from the surface. Because that the sweeping downstream takes place much faster than diffusion in the limit of high Peclet number, the temperature disturbance or the concentration disturbance is going to be restricted to only a thin region near the surface. As the Peclet number increases, the thickness of that region will decrease in such a way that if I scale the equation by the thickness of that region, then convection and diffusion continue to be of equal magnitude within this region, even as the Peclet number becomes larger and larger, so that it is possible to impose boundary conditions. We had seen that for the flow past a flat plate, where we had derived the equations in terms of a similarity variable, the variable delta here. The similarity variable had been defined as a cross stream distance divided by a boundary layer thickness delta. That boundary layer thickness delta is a function of the streamwise distance x. Okay. How do I find that function? I express the equation, all terms in the equation, in terms of the similarity variable, rewrite the equation, and then I will get an equation with a convection term on the left and a diffusion term on the right. The prefactor of that convection term does depend upon x, and for the equation to be a similarity equation, it should not depend on x, therefore, that prefactor has to be a constant. And from that you can get what is the boundary layer thickness. Okay. The other part of the equation, the temperature in terms of the similarity variable, okay, can be solved, and you get a solution for the temperature in terms of the similarity variable. Using that, you can find out what is the flux, and therefore, what is the Nusselt number. Okay. We had done that for a flat plate in this case. We had got an explicit expression for the flux, and from that we had got a correlation for the Nusselt number, okay, as a function of the Prandtl number, if you recall. We had done it for a spherical particle as well, okay, where you have flow past a sphere. The concentration on the surface of the sphere is higher than that in the fluid that is flowing past the sphere. in the limit of high Peclet number defined as the ratio of convection and diffusion, the concentration disturbance is going to be restricted to a thin region near the surface of the sphere. At the upstream direction, that thickness has to be finite. Okay. Write the equation once again in terms of a similarity variable, okay, and determine that similarity variable from the condition that within this thin region, right, the equation that I get in terms of the similarity variable, okay, it has a coefficient in the convective term which depends upon the downstream azimuthal angle theta. Okay. That has to be a constant. We can choose any constant, because in terms of the similarity variable the solution will depend on the constant, but back in terms of the original variable it will not depend on that constant. We choose that to be a 1 for without loss of generality. The rest of the equation is the concentration in terms of the similarity variable. That is universal for any surface which has a no slip condition. This equation is universal. What changes is the equation for the boundary layer thickness, and that has to be solved in order to obtain what is the boundary layer thickness as a function of distance. And that solution actually told us that this boundary layer thickness, okay, it goes to infinity at the downstream section. Okay. If you recall, when I drew the boundary layer for you, the thickness was finite, okay, upstream, but in the downstream section that boundary layer thickness goes to infinity. On the upstream side, the flow is incident on the particle and diffusion is outward. The balance between these two gives you a finite boundary layer thickness. On the downstream section, the flow is outward and diffusion is outward, and that convection takes the concentration to a large distance downstream of the particle. That distance goes to infinity as you go towards the downstream axis, okay, of the particle. That results in a concentration wake at the rear of the particle. The boundary layer thickness is not finite there, and you have to do a different analysis in order to find out what is that boundary layer thickness. Nevertheless, in order to find out what is the transport rate, we do not really need to do all that. Okay. All we need to do is to solve the equation and then get the flux, okay, and then from that we will get the correlation, okay, for the Sherwood number as a function of the Peclet number. In both cases it goes as Peclet number to the 1/3 power, because we have a no slip condition at the surface. We did the problem of the flow past the flow past film, which we had already done before by drawing an analogy with the instantaneous change in the concentration at the surface, where the concentration is changed instantaneously. We drew an analogy with that, the temporal variation in that problem and the spatial variation in this one. We can do it this way as well. In both cases, the boundary layer thickness actually goes as Peclet number to the -12. Okay. That is because the velocity is finite close to the surface, and I have two derivatives with respect to the boundary layer thickness here. Okay. And because of that, I will get a boundary layer thickness that goes as Peclet number to the -12. And consequently, the Sherwood number or the Nusselt number will go as Peclet number to the +12. Okay. This is true for any surface which has a non-zero velocity at the surface, where the flow is convected at a finite velocity at the surface. In that case, the convective term is proportional to the velocity itself. The diffusive term goes as two derivatives, or 1 over the boundary layer thickness square, and therefore the boundary layer thickness has to go as Peclet number to the -12, and the Sherwood number or the Nusselt number goes as Peclet number to the +12. And that is true even for the flow around a bubble. Okay, we had solved that problem as well and got the correlation for the Nusselt number versus Peclet number. And then last class I had briefly shown you that all of these can be placed in a common framework. The flow is in the x direction, streamwise direction, cross stream direction is y. There is a condition on the velocity that the divergence of the velocity is equal to 0, which implies that partial ux by partial x plus partial uy by partial y is equal to 0, okay, in 2 dimensions. So, if ux is proportional to y, no slip condition, ux has to be 0 at the surface relative to the surface. So, if ux is proportional to y, then uy has to go as y square. Okay. For no slip condition, ux is proportional to y, uy has to go as y square. In that case, the equation for the concentration or temperature field in terms of the similarity variable all has exactly the same form. What changes is the form of the boundary layer thickness as a function of the tangential and normal velocities. Okay. So, the only thing that changes in my flux relation is the boundary layer thickness. The Peclet number to the 1/3 power remains, and this solution for the concentration remains when the velocity increases linearly with distance from the surface. Okay. When we have a slip condition at the surface, the velocity is non-zero. Therefore, if the tangential velocity is non-zero, normal velocity has to increase linearly from the surface, because at the surface itself the normal velocity has to be 0 due to the no penetration condition. In that case, once again we get a common framework for the equation for the concentration field, okay, as a function of the similarity solution. Okay. So, you get two parts here. One is the equation for the boundary layer thickness. The second is the equation for the concentration field in terms of the similarity variable. The latter is independent of configuration. Okay. The latter is independent of configuration. Therefore, the solution is also independent of configuration when expressed in terms of the similarity variable. What changes is the equation for the boundary layer thickness. That we can calculate for individual configurations and thereby get what is the Nusselt number or Sherwood number. In this case, both have to scale as Peclet number to the 1/2 power, because the boundary layer thickness scales as Peclet number to the -1/2 power. So, that is the summary of boundary layer theory for flows past objects or flows through pipes, channels, flow of falling films and so on. In all of these cases, no slip boundary condition, boundary layer thickness goes as Peclet to the -1/3 power, the Nusselt number, Sherwood number goes as Peclet to the +1/3 power. Non-zero tangential velocity, slip condition, zero stress condition, the boundary layer thickness goes as Peclet number to the -1/2, and therefore, the Nusselt number, the Sherwood number goes as Peclet number to the +1/2. In this class, I will look at one more problem where convection causes rapid transport of material, okay, and that is goes by the name of the Taylor dispersion problem. So, if for example, I had a pipe flow, okay, this is the x direction, this is the radial direction. Okay. The pipe wall is at r is equal to capital R, okay, and I will assume that we have a laminar flow in the pipe, a parabolic velocity profile. This we had already derived earlier. Okay. The velocity ux is equal to 2u into 1 minus r by r the whole square, okay, where u is equal to the average velocity. Okay. The velocity averaged over the cross section. Okay. I can also write this as 1 over pi r square divided by the cross sectional area, okay, integral 0 to r, okay, 2 pi r dr into ux, which is a function of r. Okay. Recall that for a cylindrical system, okay, the area element in this cylindrical coordinate system, okay, is going to be equal to 2 pi r dr. Okay. It is equal to the perimeter times the thickness of this shell, okay, 2 pi r into dr, where dr is the thickness of the shell. So, I have to multiply the velocity by the area, integrate over the entire, okay, cross sectional area of the pipe and divide by the cross sectional area, that gives me the average velocity. Okay. We had derived this parabolic velocity profile earlier. Okay. Now, the question that we are going to ask in this particular case is that if I had some material that was introduced into the pipe, okay, at a particular location, okay, as the flow convects it downstream, what is the rate at which there is dispersion in this in the axial direction, okay, along the flow direction? What is the dispersion along the flow direction? Okay. Simplistically, you might think that for the diffusion along the flow direction, the equation is just going to be of the form partial C by partial T is equal to d partial square C by partial Z square, where d is the diffusion coefficient, okay, where d is the diffusion coefficient. Okay. You might simplistically think that that would be actually what is the equation, okay, for the dispersion along the Z direction. Okay. This is the convection unsteady diffusion equation. However, we do have convection here. Okay. The concentration is also convected as it goes downstream. Okay. That convection is happening at different rates at different radial positions. Okay. The convection along the center of the pipe is happening much faster. Okay. The convection, okay, in other regions happens slower. At the wall of the pipe itself, the convection is 0. Okay. So, therefore, if I look at this little element of the solute that was introduced at that location within the pipe, after some time, okay, this is going to look, okay, as it moves downstream, it is going to look something like this. Okay. It is going to be distorted due to the mean flow, because the convection is happening with different velocities at different locations along the pipe. Okay. That is going to distort this shape. Now, in this configuration, if it were just moving as a plug, okay, if it was just moving as a plug without any velocity change, diffusion will happen only in the axial direction. Okay. Okay. So, that after some time this will be diffused. Okay. So, let me contrast this case. Okay. So, let me draw the plug flow case here. Okay. If I had a constant velocity profile, okay, velocity was a constant, okay, and if I had something like this, okay, a plug of solute introduced into the pipe, okay, okay. After some time, diffusion would happen only in the axial direction, because the velocity is a constant everywhere. There is no distortion of this shape due to the velocity of the fluid. So, after some time, basically what will happen is you will have a more diffuse plug here, okay, okay, because of molecular diffusion along the axial direction. Okay. You will have a more diffuse plug here because of molecular diffusion across along the axial direction. Okay. So, if I drew the concentration field here, okay, if it was a sharp function at this location, okay, it would be diffused out at this location, okay, only due to molecular diffusion. Okay. That molecular diffusion happens only in the axial direction along the x direction. In this case, since the plug has now been distorted, okay, there can be diffusion not just in the axial direction, but also in the radial direction. Okay. From this plug you will have diffusion in all directions. Okay. So, there will be radial diffusion as well and axial diffusion as well, and that diffusion happens because the mean velocity has distorted this plug and it has changed its shape in such a way that axial dispersion, axial diffusion is important. Okay. So, therefore, because it is being distorted by the mean flow, I have to take into account convection as well as radial diffusion. Okay. So, I will have plus okay, and I have to have the convective term here. So, let me just write that. This is the complete equation. Okay. and I will consider the case where the convection along the x direction, my apologies, this should be the x direction. Okay. I will consider the case where the convection along the x direction is much larger than diffusion along the x direction. That is the high Peclet number limit that we have been considering throughout this course, okay, where convection along the x direction is much larger than diffusion along the x direction. We will come back and see the conditions under which this approximation is valid. Okay. So, what I will do is I will neglect the diffusion in the streamwise direction in comparison to the convection in the streamwise direction. Okay. So, I will neglect diffusion in comparison to convection in the streamwise direction. However, as we know, in the limit of high Peclet number, diffusion in the cross stream direction has to be important. Okay. The diffusion in the cross stream direction has to be important. That results in this spreading in the cross stream direction, and the fact that you have distorted this plug here implies that the spatial extent is now much larger than the spatial extent that I would have in this case, because the mean flow has distorted it. So, it has spread out over much larger spatial extent, and in the cross stream direction the concentration has been equalized due to diffusion. So, because of that you can get diffusion which is much faster than you would have had in this particular case, okay, if you just had a plug flow. Okay. So, how do we solve this problem? Okay. First thing, I will scale my variable r star is equal to r by capital R, okay, ux star, okay, which is equal to ux by u, okay, which will be equal to 2 into 1 minus r star square. Okay. We do not yet have a scaling for the x direction, we will just leave that as it is, we will leave the x direction dimensional for now. Okay. We also do not have a scaling for concentration, we will leave that as well dimensional for now. Okay. So, therefore, I will have partial c by partial t, okay, plus, okay, that is my equation. This should be x. Okay. Now, rather than looking at it in a fixed reference frame, it is more convenient to look at it in a reference frame that is moving with the mean velocity of the fluid. Okay. So, therefore, rather than looking at it in a fixed reference frame, I look at it in a reference frame that is moving with the mean velocity of the fluid. Okay. So, this is, okay, and this is my initial plug. Okay. This is at some later time. Okay. And that mean position has now changed. Okay. The mean position of that plug has now changed because it has convected, okay, because it has convected downstream. Okay. Therefore, I can define x prime is equal to x minus ut. Okay. So, that as time progresses, okay, the origin of this coordinate system is in a reference frame that is convecting with the mean velocity. Okay. The distortion is actually quite large. Okay. I have sort of drawn it here like this, but actually, okay, if you actually draw the distortion, it is actually quite large, because these points are not moving, they have 0 velocity. Okay. The walls of the pipe have 0 velocity. So, with time the distortion actually looks something like this. Okay. The velocity is 0 at the two ends and is maximum at the center. So, the distortion is actually quite large, okay, in this plug, and coupled with that you have diffusion in the radial direction. Okay. And that is what causes a large axial dispersion, as it is called. Okay. That is what is called causes a large axial dispersion. Okay. That is why it is called the Taylor dispersion problem. So, So, I will express everything in a coordinate system that is moving with the mean velocity of the fluid. So, in that case, okay, partial by partial t is equal to partial by partial x prime. Okay, so, partial x prime by partial t, okay, is equal to minus okay, and partial by partial x is equal to partial c by partial x prime, because partial x prime by partial x is equal to 1. Okay. So, the equation now becomes minus u partial c by partial x prime plus 2 u into 1 minus r star square. Okay. That is the conservation equation. Alternatively, I can write this as u into 1 minus 2 r star square okay. So, I can write this as u r square by t. Okay. Now, I can express the concentration field as a cross section averaged concentration plus the radially varying part. Okay. So, if I plot the concentration field as a function of the radial distance, okay. If I plot the concentration field as a function of the radial distance, okay, I am going to have some concentration variation. Okay. They will have some concentration variation from the center to the wall of the pipe. Okay. I can write that as the sum of the average concentration plus a variation part. Okay. Okay. So, I will write the concentration as C bar plus C prime, okay, where C bar is the average concentration. We had just defined the average concentration, okay, 1 by pi r square integral 0 to r, okay, 2 pi r dr times C. Okay. Or if I express it in terms of the scaled radius, okay, r star dr star, this can also be written as 2 integral 0 to 1, okay, r star dr star times C. Okay. Okay. Where this factor of 2 emerges because I cancel out the pi here and the area element has a 2 pi in it. Okay. So, this is the average concentration. Okay. So, what that implies is that the average of the okay, so this average concentration is only a function of x. Okay. So, the original concentration was a function of r and x. Okay. This average concentration is only a function of x, and therefore, I have this additional part which is a function of r and x. Okay. I have this additional part which is a function of r and x. Okay. Since the average value of the concentration is equal to the area times is the average of the radial concentration. Okay. For this second part, the average has to turn out to be 0. Okay. For the second part C prime, the average has to turn out to be 0. Okay. So, the condition for C prime is that integral 0 to 1, okay, r star dr star C prime is equal to 0. Okay. The average of the departure from the area average concentration, if you take the average of that, that has to be 0. Okay. So, I will express the equation in terms of this average concentration plus the radially varying part, okay, and then solve the equation, and then we will see if we can get an equation, a diffusion like equation for this concentration field, where this radial part of the spreading of the concentration results in an enhancement of the axial dispersion. Okay. The radial diffusion coupled with convection results in an enhancement of the axial dispersion. We will continue that in the next lecture. Okay, I will see you then. In this particular problem, I will be making a few approximations in the next lecture, but I will justify them as I go along. We have already made one such approximation, that the axial diffusion is small compared to the radial diffusion. We will make other such approximations and then we will come back and see. So, I will see you continue this in the next lecture. I will see you then.